going to talk about, in that vein, okay, of non-optical microscopy of, in this case, ovarian and breast cancer.
Hi, great. I'd like to thank Eric for the very nice introduction, and also for having me here. This was a place I wanted to visit for a long time. So, start by thanking my co-workers. Some are past and present from the University of Connecticut, and some are current at University of Wisconsin. I just moved about 6 months ago. So we've been working on ovarian cancer, will be the bulk of this talk. And breast cancer, I should put in quotes, because what I'll show you is just some in vitro models here, but this is pretty recent work. And then most of this work has been paid for either by NIH or NSF. So the 3 parts of today's talk will be, the first part, the bulk of it will be on SHG imaging of human ovarian cancer, and then SHG imaging in some gel models for breast cancer. And then the last part of the talk will be on adhesion and migration dynamics of ovarian cancer cells on using nano and microfabricated models, the ECM that we put together. So what I start off talking about is changes in the ECM that happen in ovarian cancer. These have been documented in several cancers, ovarian, breast, colon, and where there's often a classic desmoplasia or upregulation of collagen that's seen. So we asked the question by, can we use SHG to really get at some of the changes on the small scale, the fibril and fibril levels assembly in the ovarian stroma. So the levels we need to think about is, well, we have collagen, starts off a collagen molecule, which are really small, so we can't see those. And then these self-assemble into collagen fibrils of diameter roughly 50 nanometers, which we can't see either, but I'll show you we have some metrics that we can infer some of the information of how these are put together. And then also we can image directly the collagen fiber level of assembly. So what we're going to do is, so I'm going to show you here on ovarian cancer, these will be all ex vivo tissues from human ovarian patients. And so what we're going to look at is that we take a piece of the biopsy that our clinical collaborator Molly Brewer took out, and then we're going to cut off the surface epithelium, and we're going to image right below it. So we're going to image the first couple hundred microns below the stromal, and for this part of the talk, we're going to ignore the epithelial part. So what we do is our SHG microscopes, and I'm just clipping a little bit. And so we start this off. It's built around a commercial flow view scanning head. Then we add a bunch of parts that we need. We do a lot of polarization analysis, and I'll show you some of this. If we control the laser input polarization and then analyze the signal polarization out, there's structural information that's encoded there. And so for routine imaging, most of it I'll show you, we use circuitry polarized light because that captures all the orientations of the fibers equally. And then we add match detectors in the forward direction and the backwards detection. And some of what I'll show you is analyzing the ratio of the forward to backward signal. And I'll go through that. This will give us some information on the fibril level of assembly. Okay, so just start off with a couple optical sections. So the field size is here about 200 microns. So this is an optical section from normal ovary, and you can see that you get kind of a random crosshatch structure. And then if you look at a malignancy, you see something that's totally different. We see these very regular helical structures that are very long. Now, if we look at different patients, the normals pretty much always look the same between patients, even within the same patient and between patients. And the cancers also always look the same. And if it's the case that we don't have a lot of good tools to deal with, are those that are high risk. And these are actually the ones that are most important because the penetration of ovarian cancer is only about 1% in the U.S. But for women carrying a BRCA mutation, that number goes up by about 30%. And most of those patients will die. So ultimately, we really like good metrics to figure out what's going on with the high-risk patients. We don't really have that yet, but I'll just show you why that is because there's a lot of heterogeneity. And so this is from a high-risk patient. In this case, this kind of looks more like the normal case. Then if you look at another section, this is from a different patient, but now this one looks more like the cancer. But even if you look at the same piece of tissue from the same patient, you get this kind of heterogeneity. And so we're exploring some signal processing methods to try to do that. We've not been very successful yet. So what I'm going to show you today is just delineating the extreme cases of normal and cancer. Okay, so these are 3D renderings and comparing the ancient histology. So this is normal. So this is a section about 200 microns thick, and a section about, that were put back together. And so the collagen is here. The holes are where the ovarian, the stromal fibroblasts would be. Then if we look at the ancient histology from the same tissue, this is the top going down. And you see the same thing. You see the pink is the collagen, the blue are the nuclei. So we see this kind of a mesh-like structure. And when you look at the 3D rendering of cancer, you see these long helical structures that we saw in the single optical section. And these look very, very dense. And then if you look at the ancient histology, now we have some cells here below the surface, but this is really acellular compared to the normal. And it's also very bright. If you compare the intensities in these thin sections between the normal and the cancer, they're different by about a factor of 4 in intensity. So the SHG is a convolution of how much collagen there is squared, and then also how well it's organized. And so we haven't been able to decouple those things very well yet. But clearly looking at the histology, there is certainly more collagen that's here. Okay, so I want to go on and just understand why these structures look different as opposed to just by visual inspection. So what I'm going to show you is what we dubbed an integrated metric. And so the measurements that we do, so we measure the 3D dependence of the signal directionality, which would be the forward-backward ratio, and then also the attenuation of how the light decreases as we get further and further into the tissue. So this is a convolution of two things. So there are what we call SHG creation attributes, which is the initial signal directionality of how the SHG gets made, and then how it propagates based on US and G at the SHG wavelength. And both of these depend on the fibrillar structure. And then we also measure separately offline, we measure US and G. And then we do a Monte Carlo simulation of these responses, because all we do is measure photons. Because these things are convolved responses, we don't know from whence they came. And in general, either or both the creation attributes or the propagation could be different in diseased tissues. And so what we want to know is what would be the best diagnostic signature. So first we measure US and G offline using integrating spheres. And so we see a couple of things that are interesting. So these are representative optical sections for the cancer and for the normal at both the lambda SHG and fundamental wavelengths. And what we see is that US is about 1.5 times bigger for the cancer than for the normal. And that makes sense because US is basically a measure of density. And just looking at the 3D renderings and histology, the cancer definitely looks more dense. But the other thing that we also see is that if you look at the comparison of US prime over these two different wavelengths, and this is just 2 points, but what we see is that the decrease in US prime between 450 and 900 is about a factor of 1.5. And then the decrease of US prime between the normal and for the normal at the SHG and fundamental wavelengths is about a difference of about a factor of 3. So I'm going to use these values and Monte Carlo summations in a little bit, but I also just want to mention the spectral dependence of US prime. And I stress we only have 2 points. So μs is the scattering coefficient, and so it is 1 over the distance of how far a photon will travel before it hits something and scatters and changes direction. So that's really mostly a measure of density. It factors into the attenuation. But then there's also G is the scattering anisotropy. So that is the direction of the scattering. So if you have tissues that are really well ordered, say you have something like tendon, almost anything that scatters off tendon will go in the forward direction. Now, if you have something like brain that's really random, then you get more of an isotropic scattering response. So yeah, right. So G ranges from 0 to 1. So 0 will be isotropic. 1 is completely anisotropic. So μs prime is the reduced scattering coefficient, which is the product of μs times 1 minus G. And so it's a couple parameter that includes both the scattering length as well as the direction. And it depends highly on the tissue structure. And so, so I just want to, and you know, the person who's probably done the most of this, and you know, use his formula here, is Vadim Bachman at Northwestern. Has really exploited what is the wavelength dependence of US prime and what it means, how that relates to tissue structure. So in general, the US prime the spectral dependence is governed by a power law, and where this is lambda to the 2m minus 4. Now, if you have m equals 0, that would be Rayleigh scattering, and so you would get a classical case of the wavelength to the minus 4. But tissues don't work that way, and this is work that Bachman did last year. Is that this factor m relates to the form of the refractive index correlation function, and that's how a measure of how similar the tissue is over distance. So if a tissue is very, very regular, its refractive index correlation function will decay very, very slowly, and if it's more random, it will decay more rapidly. So we only have, at this point we only have the laser fundamental and the SHG wavelengths, but we just do a 2-point fit. And what we see is that we get very different forms of M. So for the normal, we get something that's in the mass fractal regime. And what that means is there's no characteristic scattering sizes, but it's only a measure of how the distance over which things are self-similar. For cancer, we get a much larger value of M. This is in the 1.65, so it's a stretched exponential. And this means there are characteristic scattering sizes. And so, but anyway, what this really means is the bigger value of M means more regular. And then this is between 450 and 900.
900.
Yeah. So our laser excitation is at 900, so we're collecting the SHG at 450. So we're going to go back and fill these in now. But at this point, we only have 2 points, so this is sort of a heuristic argument. But the take-home point here is that what we get by this simple analysis is that the cancer is more regular in terms of how it scatters light. And so that's also consistent with what our SHG pictures actually look like. The cancer definitely looks more regular than the normal. And so this is unrelated to SHG, other than this is the fact that how the responses that we measure, now I'll show you in a minute, do include all these factors. But in general, this wavelength dependence is called the spectral slope, and this might be a good diagnostic for ovarian cancer. And we just got a new OPO that's tunable from 500 nanometers to 1700 nanometers. So we're going to go back and fill in all these points now that we have this. Okay. So the next part of this I talked about, we need to consider how the SHG gets made, how much of it goes forward and backwards. So there's 2 ways that you get a directionality in an SHG experiment. One is from light that gets emitted backwards directly, and we call this the idea of not considering just single fibers, but of a domain. And this can be either small fibrils or small fibers packed together very closely, or single large structures. And so how the tissue is arranged, if the laser is going this way, how the tissue is packed this way, affects how much light goes forward and backwards initially. And so in an SHG experiment from tissue, there is always going to be a direct backward component, because if you frequency double in a crystal, all that light will go forward because it's a perfectly phase matched case. Well, in tissue, that's never true, because you have dispersion in the refractive index between the fundamental and the SHG wavelength. So this has, because that's not phase matched, this has implications on how the light gets made. So as a rule of thumb, if you look at the domain of how your fibers are packed together, if they're very regular on the size scale of lambda SHG, most of that light will go forward. But then if you have something that are smaller fibers that are more random, then say lambda SHG over 10, or say in the 50 nanometer range, then you will get an equal mixture of forward backward components. And then once you make your SHG, then we have multiple scattering. And so the backwards SHG can then arise from multiple scatter of the forward direction and vice versa. And that will scatter based on the values in the previous table I showed you. So what we measure, if we measure our light forward and backwards, it's a mixture of these 2 things. And so they're involved in an experimentally indistinguishable. So either or both can be different in cancer. And we've done this for other diseases too. And, it's a pretty general approach. So the experiment, the first experiment we do is measure how much light goes forward and backwards as a function of depth. And so this is a sum plot over several patients. And so the blue is the normal, the red is the cancer. So this is the measured forward-backward ratio, and then this is the depth into tissue. And what we see in all cases is that the normal is more forward-directed. And from the slide I showed you on the scattering properties, the scattering coefficients, the normal is less scattering. So it should have a higher forward-backward ratio because the light that gets made forward has a better chance of staying in the forward direction. And we see that both these plots go up with depth, and it's for the same reason. As you get further into tissue, there's less chance that that photons that get made forward can bounce around and end up backward. So what we're going to do is then do a Monte Carlo simulation to separate out the initial directionality, which I dubbed by subscripts, and from what we actually measure that's convolved with mu, s, and g. So there's basically no cells. So this is lopping off the cells. But an ovary it mostly gets replaced by collagen. We've lopped off the epithelium. Okay, so having this, what we do is then we have a simulation approach where we're going to vary the submitted forward-backward ratio and then extract out then in the measured optical parameters to get the best fit. So to do this, we borrow formalism, the MCNL formalism from Li Han Wang and Steve Jott. Then we added the components that we need for an SHG. And so in their formalism, that was basically a plane wave. So we introduce a factor that simulates optical sectioning by considering the numerical aperture. Then we calculate the primary filter effect, which is the loss of the laser as we go through. And then we include or assume a relative conversion efficiency between the tissues, which is essentially the relative chi2 values. And that's the efficiency over which the SHG gets made. It's hard to measure that absolutely, but we can do comparisons. Then we assume initial directionality. Then we calculate the secondary filter losses based on mu, s, and g. And then we count how many photons go forward and how many go backwards. And that will let us to decouple that. So if we do that, and so this is the experimental data I just showed you with the corresponding the best fit simulations. So this is the cancer, this is the normal. And what this shows is the best fit was that the normal was about 93% forward, that's about 13 to 1. And then the cancer was 77% forward, that's about a 3 to 1 ratio. So these initial forward-backward ratios are very, very different for the cancer and for the normal. So that implies there's a large change in the fibril assembly. And so it's nice to be able to fit something, but we need to have a physical comparison. So what we can do is look at the EM. So these are TEM images of the cancer and of a normal. And so what we see in the cancer is that we get something that's very regular, that all the fibrils are pretty much the same size and they're pretty well packed. Then if you look at the normals over here, the average size is actually about the same, but there's a broader distribution. You get some ones that are smaller, some that are bigger, and then they're also more randomly spaced. And so, based on some theoretical work we did, is that this structure should give you a lower forward-backward ratio than this does. So this is what we measure, what we extract from our simulation is consistent with this mathematical model that we put forward. So that's a nice thing. The scale bar is that's in MAD, but the size scale here, I think the most probable was about 60 nanometers. So we can't directly measure the sizes of these fibrils because they're 50, 60 nanometers, so they're way sub-resolution. But we can infer something about how they're put together through this forward-backward measurement and simulation approach that we have. So the next measurement we do is measuring the attenuation. And so this is going through the first 100 micron slice. So we take the biopsy that our collaborator gave us, cut off the first 100 microns, and then image that. and then image how the SHG as it goes through. And here we didn't get so lucky. So here's the normal is in blue, the cancer is in red, and they are exactly the same. So we just decided to go back and also try to simulate this and figure out why they were the same. Now this response is actually a complicated response because it depends on, we have to do this relative between tissues to scale. So these are all normalized. So this response is governed by how the laser goes through. And it actually turns out the imaging depth we get in this is actually governed by the loss of the laser, not by the SHG coming out. Because the quadratic dependence of the loss of the laser going through, that dominates over the slightly decreased scattering at the SHG wavelength. So it's really, this plot is basically a measure of the primary filter response, or squared. And because if you simulate this including the SHG, you actually get the loss of the primary filter and loss of the primary filter plus the secondary are basically the same. But at any rate, so we need to simulate this to see what's going on. And so what happens here, we just got really unlucky. We had absolutely offsetting parameters. That if you, so what we did here is that we have to assume relative Chi2 or SHG conversion between these tissues. And from thin slides, that was about a factor of 4. So if we include that in our simulations and then include the bulk optical parameters we measured from this table, and then factor all that in the simulation, this is the experimental data and the solids parsed a little bit. And here's the simulated data for the normal and cancer in the open circles and open squares. And they don't perfectly overlap with the experimental data, but they follow the same trend, is that the simulated data for both the normal and the cancer are pretty much overlap with each other. So what happened here is we had a direct offsetting response. Is the cancer is more scattering. So it should have, its attenuation should have decayed faster than the normal. But it was 4 times brighter to start off with. So that swings it back the other way. And so it ended up being a wash. But I think all's not lost, because now that, some of this is wavelength dependent. Because I showed you earlier that the spectral dependence of mu(s) prime is different for the normals and for the cancers. So now we have a new OPL and bring a new microscope to do longer wavelength imaging. At longer wavelengths, we actually might get a differential response between the normal and the cancer. And that's nice, because this is the kind of, even though this is showing the forward attenuation, we can just as easily do this in the backward direction. There'll be less signal, but we can measure the attenuation going backward, and it has all the same components. So this is something that you could do in vivo through an endoscope pretty easily. Well, not easily, but more straightforward than the directional part, which I think can be done too by means. But this is something that could be implementable more directly. And so the last part of this is looking at that was pretty much on the assembly of fibrils and how much collagen there was. Then another measure we can do is looking at how aligned the fibers are. And so if you look at the SHG polarization anisotropy, now this is a different anisotropy, but it has the same units. It's sort of philosophically related. The way you do this experiment is you fix your laser polarization, and then you have a polarizing analyzer in the detection path, and then you take 2 images, one parallel to one where the detector polarization is parallel to the laser, one where it's perpendicular, and then you use the anisotropy formula. In the limited cases, our beta of 0 will be isotropic, in which case you probably won't get much SHG anyways. And then beta of 1 will be completely aligned. So these are analyzed single sections from cancer and from the normal, and we get the cancer has a significantly higher anisotropy than the normal does. So just kind of the point of this part of the talk is to sort of ask the question: is this remodeling of existing collagen or new collagen synthesis? And so all the data we have indicates that the collagen in the cancer is more ordered, because the fibril shapes are more regular. The fibril diameters are more normal. There seems to be more collagen, even though we haven't definitively proved this. And based on the spectral dependence of mu(s) prime, it also would indicate that the cancer has a more regular structure. So in general, it's hard to imagine that nature would work to decrease its entropy by making things that are less ordered to more normal, to more ordered. So this is what we're seeing is probably all new collagen synthesis, and so kind of like you guys say it must I know it happens in breast cancer, where there's large changes in the kind of ECM. I think the effect here is clearer. This is basically the stroma gets replaced by certainly changes to this different order collagen. But ultimately, understanding the temporal sequence of this remodeling may ultimately guide treatment strategies, and hopefully, understanding sort of the limiting cases of the normal and cancers, we can start gaining some insight in what happens in the patients who are high risk. Yeah.
As you get older,
we don't have enough data to say. These are fairly small. These are only about 5 patients each, so we don't have that level of data. Yeah, I think all these were postmenopausal. I don't know how old they were, but they were all postmenopausal.
Because there's a significant change in extracellular matrix going pretty close.
Right. So, our grand hope in all of this is to, once we figure out what's going on, is that you could never do any of this to screen the general population. It's just too slow and too invasive. But for the women who are at a high risk, you could at least consider screening them every 5 years or so from premenopausal on. And you could do that through a laparoscope. I don't think there's any way we could do this non-invasively, but I think it could be done minimally invasively. But for women who have a 30% lifetime chance of getting ovarian cancer, that may be an acceptable thing. But we're out. Yeah. Oh wait. Yeah.
Correlated with anything that's anatomical. Like when you talk about kind of random, but then this definite directionality. What's it pointing from or to? There's either cells responding to a new mechanical tube polarized or they're refusing to molecular source of the same.
I have no proof of anything. My suspicion is that the cancer cells are directing the shell, that they're actually using those helical structures for migration.
Do you think those fibers may be emanating from the tumor cell? Just in a total accordance.
But it is interesting though, because it looks the same everywhere you look. And because even if you look at even 200 or 300 microns down, it all looks the same. And so it's really interesting because it's not an epithelial tumor, but there's I almost hate to say this, but I think there is a large field effect here, and I don't know from which it emanates, but it is my suspicion that the cancer cells are directing that somehow. Now, unfortunately, all the data I have is from patients who are stage 4, so we don't have any data on earlier cancers. So. I mean, it would be really nice to have that data, so to see what it looks like, kind of as an early cancer. We don't have it. But I'm writing a grant to try to go after this using combination imaging and some in vitro models of using cancer cells, and then some tumor models as well, and then including some stromal fibroblasts and see how that plays out. But as of now, I don't know. I don't know how it works. That's so at this point we've kind of done the physical analysis. So the next step of this is actually try to get at more of the underlying biology. Okay. Okay. So the next thing I want to show is just a short vignette on breast cancer imaging, and this is some early work that was done by my new colleagues Patty Keeley and Kevin Elisari. In mouse models of breast cancer, where they identified three time points they call TACs, or tumor-associated collagen signatures, where they call TACs 1 is just sort of a classic desmoplasia or deposition of collagen, and then TACs 2 is sort of early, more kind of intermediate phase cancer, where the tumor boundary is here, and then the collagen is here. And in this case, the cancer cells do pull on that collagen and align it. And then also an invasive stage they call it TACs 3, where the tumor boundary is here. Now here they're parallel to the tumor boundary. Here, the predominant alignment of the collagen fibers is perpendicular. So Patty and Kevin have really good data on all these things in several mouse models, and now maybe some in human tissues as well. But we recently asked the question, this is all type 1 collagen that we've been thinking about in most tumors. But there's some evidence going back a ways that there's type 5 in breast cancer. And there's no type 5 collagen in normal stroma, but it can get up to 10 or 20% in basic breast cancer. So, and then some later works from Burke showed how the interaction of type 5 and type 1 regulates the diameters of in vitro self-assembled fibers. So this is TEM of type 1. It shows the regular banding pattern. Then the EM of that's all type 5. It lacks periodicity. They're random. They're thinner. Then if you do an intermediate case of 70% type 1 and 30% type 5, you get something that's in between. So again, these are all sub-resolution. So we asked the question, is SHG sensitive to these kind of sub-resolution changes? So we've been making some mixed gels of type 1 collagen and type 5 collagen, and doing the same kind of metrics we just did. And so we've done a series of going from all type 1 collagen to 5% type 5, and then 20% type 5. And these are the Westerns. So if we just image the single optical sections from relative to these, you see that the 0% type 5 and the 5% type 5 look pretty similar. Then if you go up to 20% type 5, you see something that's the fibers get shorter, they're more closely packed. And the other thing is that this is a lot dimmer. This is actually the raw intensity. So the intensity goes down by about a factor of 4 between the all type 1 and then the 20% type 5. And so that indicates that the assembly is less ordered. And also, if you look at the fiber lengths, this is for the all type 1, 5% type 5, and 10%. This should be 20% type 5. That the fiber length also decreases. And this is actually an upper bound of what we can actually really identify by thresholding as real fibers. So we definitely have less ordered fibril-fiber structure for the 20%. So we want to see if we could. The size scales are all the same. What's different, and these, the intensity is scaled. This is the raw intensity. But yeah, the size scale is, these are 160 microns across. Size scale is all the same. So if you look at the 3D renderings, you see the same thing. These are the all type 1, 5% type 5, and 20% type 5. Again, the intensity is scaled here. So this looks more filled in, but the fibers are definitely shorter, and the SHG is a lot weaker. So we do the same directional analysis we did before. And so the one that's either 1% or 0% type 5 and 5% type 5 completely overlap in terms of the forward-backward ratio as a function of depth into the gel. And if you look at the TEM from Burke, I didn't show both of them, but in both cases, the most prominent fibril size, the diameter is about 100 microns, 120 microns. But then for the 20%, this drops to about 70 nanometers. This drops to about 70 nanometers, and it has a much lower forward-backward ratio. So the higher forward-backward ratio here is consistent with having a better order structure because these gels scatter a little bit. There's probably 1 or 2 scattering events. But this mostly reflects a higher initial forward-backward ratio, which means the fibrils were bigger and better ordered. So what we see by SHG directional analysis is consistent with the EM data. So again, much like the ovary, we can't resolve these sub-resolution differences, but we can infer them. And we can also do, I should put attenuation in quotes here because we don't really see attenuation. And the reason we don't is that these gels are not that scattering. So how the SHG goes as a function of depth is largely defined by the score of the primary filter, and these gels just don't scatter that much. So if anything, the attenuation, I'll put that in quotes, actually go up a little bit. But for the point I want to make is that for the 0% type 5 and the 5% type 5, the forward-backward ratio and now here the attenuation ratio are all the same. So they overlap very nicely. And then if you just normalize the intensity, the 20% has the same trend, but it's just a lot weaker. So all these plots are self-consistent. So we can make some assessments about how the fiber length and also then the fibril diameter change with increasing type 5. And again, this is all in vitro data, and we're going to start putting some cells in these as well. But it remains to be seen if you could actually use this as an in vivo probe. You'd have to verify it through all sort of antibody staining and such. But anyways, it is a first step. Okay, I ain't my time. So I'm not going to get through all of this, but I just want to show you some fairly recent data on. So far, everything I've done is ignored the cells. And so what follows here is actually not imaging tissue, but what we're going to do is we're going to fabricate some simple but I think somewhat biomimetic models and then look at adhesion migration dynamics of ovarian cancer cells. And so the historical way this has been done is using Boydin chambers or a flow chamber, which you take a membrane that might be coated with matrigel or laminin, and then you put cells on top, and then they count how many move after a certain amount of time or how many cross through the thin membrane to the lower surface. So that model, that kind of model provides ECM cues in terms of biochemistry, but the ECM is 3D and has a fibrillar structure that matters for how cells migrate. So it doesn't recapitulate that. So we've been trying to make some simple models to work on that. And so what we do this is now, instead of using imaging, so we're not going to use nonlinear optics now for imaging, we're going to use it for fabrication. But the idea is the same, is that much like you image, you section by multiphoton or SHG, you can also fabricate by the same way. And so what we do is that, what I'm going to show you is mostly 2.5 dimensions. But what we do is we do multiphoton excited photochemistry. Typically, we use Rosenberg, even though recently we've been using a porphyrin. And so for the case of Rosenberg, we mix it up with a solution. In this case, we'll use laminin. But then we can excite this by 2 photons, and all the population, or most of it, goes over to a triplet state. And then the triplet state can react with molecular oxygen to make single oxygen, which then can react with a protein to make a radical, and then that can form a cross-linked protein. And so, in this case, this is a circular gradient we made out of laminin, where the concentration decreases as we go radial outward. So it actually looks 2D, but it's actually sort of 2.5. These are widths of about 500 microns and also about 500 microns high. So what we're going to do is we're going to make a very simple model of the basal membrane. And so the basal lamina for an ovary is roughly half type 4 collagen and then laminin. So what I'm going to show you is just using laminin. And so we're just going to make a simple model. We're going to take laminin, what I'll call fibers, and fabricate them in parallel structures here where they're spaced about 10 microns. And this is an immunosame picture. And then we'll seed cells on them, and then watch how the cells attach and how they migrate. So they'll do that based on both the ECM cues as well as contact guidance. So the cell lines that we use are, so we did a survey. So we used immortalized normal ovarian epithelial cells. And then 3 cancer lines, human cell lines. One, these OVCAs are weakly metastatic and slightly polar. The SKOVs are moderately metastatic and fairly nonpolar. And then these Hay1 cells, which are highly metastatic and very polar. You see they have these very branched structures. And so what we do is then we seed these on one of these laminin patterns, and then we take phase contrast pictures sort of every 10 minutes over 24 hours, and then measure the instantaneous velocities of these over those 10-minute period, and then plot them. And so if you do that, what you see is a smooth increase in migration speed going from the normal cells up through these highly metastatic cells. And so these highly metastatic ones migrate much faster, but they're all different from each other. Now this is just that migration is important, and we all think it should be, but this is actually doing it on something that at least resembles, at least taking steps towards being biomimetic. We can also look at the adhesion. If we make a simple assumption that the adhesion strength is related to the focal adhesion density, is that we see the same thing, is that we get the highest adhesion for the normal cells, and then the weakest adhesion for these highly metastatic cells. And these Hay cells almost don't even form punctate focal adhesions. They just have these really branched structures. Well, at least in these 3 cases where we have enough, is that the focal adhesions localize on laminin, statistically significantly. So the metastatic potential is also correlated with decreased adhesion strength, and so suggesting that exfoliation is an important part of the metastatic process. And my clinical collaborator, Mallory Brewer, said when she operates on patients, sometimes she just really sees these cells really just kind of flop off. And if they do that, then they can go anywhere in the intraperitoneal cavity and reattach and form that metastatic tumor. Okay, so those were fairly simple experiments where we were really providing mostly contact guidance because, well, in addition to the binding, but those were structures of constant intensity and constant concentration. Recently, we started thinking about making gradients because haptotaxis has certainly been implicated in terms of metastasis. And also, just in terms of general cell biology, I think it's an outstanding question. If when cells, in hepataxis, if cells are responding to local concentrations or they're responding to the slope. And so what we're going to do is we're going to use the same technology, and now we're going to make some linear gradients. And we're going to examine the up-down preference of those different cell lines. So how we do this is that we also do this by laser scanning. And what we do is we make a ramp. So we do this size between, of how far the galvos move, and over a range of 800 microns. And so this is an immunofluorescence picture. So at low concentrations, the points are actually discrete. So we make really big spacings between galvo steps, and then we make those progressively closer and closer together. And so about halfway through this gradient, that these end up being continuous structures. But now the step size becomes smaller, so that effectively increases the dwell time and increases the cross-link density, so we get more laminin. In this case, this was actually for fibronectin. But if you do the immunofluorescence and then fit this to a slope, you back out what the concentration was. But we can get a range of concentration approaching about a factor of 40 over 800 microns. And so then we also did the same thing we did before, is measure the average migration speed, just to make sure that this works the same on the gradient as it did on the continuous structures. And we see the same trend. So this is the migration speed. So this is on a gradient that was had a dynamic range of 10, and these are gradients that had a dynamic range of 40. And so we get an increase from the normal cells to those that are somewhat metastatic to the Hay cells move really fast. And then the same on gradients that have a range of 40. Okay, so now we actually want to just really look at the haptotactic process part of it and see how the cells respond to these. So what we do is we do these experiments over 3 days, and so what we do is we just look at the cells when they start, and then 3 days later from where they initially started, we decide if they went up to higher concentrations or down to lower concentrations. And what you see is that for these alpha cells on a 40-fold dynamic range gradient, we get about a factor of fourfold preference for those that went up versus those that went down. And we also do see contact guidance. If we model this as an ellipse, then measure the angle between the major axis of the ellipse and the gradient direction, we get basically a distribution that's peaked around 0. So the cells line up parallel to the gradient. Then what about the slope? So if you look at a gradient that's got weaker slope, here that's got a 10-fold dynamic range, now we still get a preference, but now our preference, instead of being a factor of 4, our preference is about a factor of about 1.5. So the slope matters, at least for these cells. And we've done other things looking at migration on different series of concentrations. I showed you those constant concentration linear gradients. So, but it turns out that both matters. The local concentration matters and the slope matters. But it also depends on the cells you're looking at. So if you look at these SKOV cells, these are nonpolar. Those alpha cells are reasonably polar. And so if we look at these nonpolar SKOV cells on the 10-fold gradient, we get a statistical preference, but it's not much. Then if we do this over a range of 40, we're back to having about a 4-fold preference. So here the slope matters a lot. And my sense is it matters because these cells are not very polar. So they actually need an additional cue to kind of push them in the right direction. And so then if we do the same thing with these highly metastatic branch cells, what we see is on both the 10-fold dynamic range and the 40-fold dynamic range, we get basically identical response. So here the slope doesn't really matter at all, probably because they're really polar to begin with. So I think, as asking in terms of the cell biology question, is the slope of the local concentration, I think is actually too simple. I think it also depends on the cell polarity, at least based on this series of experiments. And so we can also look at the cytoskeleton dynamics. And so if you look at the cytoskeleton distribution of these gradients for the SKOV cells, we've done it for all the lines. At low concentration, we get a random distribution of stress fibers. This is a polar plot of the stress fiber distribution relative to the gradient axis. And then we can also count the number of focal adhesions that are on the laminin versus that are off. And we don't get a statistical preference here at low concentration. Then if we do this in the medium concentration range of the gradient, we look at the polar plot of the F-actin distribution. Now the stress fibers really line up relative to the gradient. And then the focal adhesions are also preferentially on the gradient as well, and by about a factor of 1.4. But the part that's the gradient versus the empty space is actually pretty small, so this is actually a statistical difference. Then if you look at high concentration, it's even more in the same direction, that we basically get stress fibers that are really parallel to the axis of the gradient. And now we get a strong distribution of the focal adhesions being aligned on the laminin versus off. What's up?
Well, it's not laminin, what's the other?
Oh, I'm sorry. It's actually not. So it's a self-assembled monolayer BSA. We do. I mean, it probably gives us less contrast than other things would, but because it's not cell repulsive. The cells will stick to it, eventually make their own matrix, but it's not specific either. What's that? The integrins will not recognize BSA. Now the cells make their own matrix, and then on top of it. But
Going back about polar and non-polar.
yeah,
Can you explain that?
the shape.
Shape.
So yes, in terms of cell polarity, something that's round is nonpolar, elliptical is nonpolar, and things that are really branched are polar. Where it basically means one end of the cell is different than the other. Okay, so the last thing I'll show you is a couple movies, because the one thing everything we've done so far is really just look at the cell matrix part. Well, we also can start thinking about the cell-cell interactions. These are epithelial cells, and we'll talk to each other. So we took movies over 3 days to see if we see collective migration. And I skipped over on the intro slide here, but one of the ways that cancer can metastasize is the cells can actually move together into the stroma or also on top. So on these gradients we looked at collective migration, and here the low concentration part of the gradient is here. It goes this way. So this is data for about 3 days. So these are these weakly metastatic cells, and so they just kind of move up and down, and very parallel to the gradient. And there's a couple that start to form cell-cell junctions, but there's not a lot. So for these weakly metastatic cells, the cell, at least in these time frames, the cell matrix interactions are dominating. If we look at these weakly metastatic cells, we start to see some collective migration. Now the gradient again goes from here up to here, and so again this is over 3 days. Now we start seeing some of these cells merging. And they're not completely moving together, but they are starting to a little bit, but they're definitely forming little microtumors. Then lastly, oops. So in this case, these are these hay cells. Now the gradient goes this way, and after 3 days, these cells really move together, and all the initial cells we started with really merge together, and most of them end up, this is the high concentration part of the gradient. So after 3 days, most of those really form together. So the cell matrix directs the initial migration, but initially they all find each other and then start moving towards higher concentration. I'll skip that. And just close here is that some sort of general conclusions from this part of the talk is that we see increased migration speeds for the more metastatic ovarian cells and decreased adhesion, suggesting both the migration and exfoliation are important parts for metastasis in vivo. And so these nanostructured concentration gradients direct both the cell morphology and the cytoskeletal properties. That in all cases, the cells become more aligned, and their cytoskeleton become more aligned with higher concentration. And then, at least in the series of experiments for the ovarian cancer cells, is that the local concentration and slope, the gradient govern the haptotactic response. Well, it also depends on the cell polarity, and continuing these experiments may give us some insight into metastasis. And also, these gradients are useful for studying haptotaxis because we can study both the initial cell matrix part and then the cell-cell interactions. So with that, I'm done, and I thank you all for your attention and happy to answer any questions.